Yes, sir. Audible.
Present, sir.
Present, sir.
Present, sir. Present, sir.
Present.
Present, sir.
Hello, sir. Honakanksha is present.
Yes, students, I hope I am audible and the slide for the MIPS processor is visible to you. Yes. Am I audible or not?
Yes, sir.
Hmm? Okay. So let us go for the uh, MIPS processor. So this particular MIPS processor is one of the processor whose architecture we shall be studying here, and it is one of the processor which is of the type RISC type, that is reduced instruction set computing type. So there are two types of processors. Uh, RISC type of processor, reduced instruction type kind of processor, and the other one is the sys type of processor, that is complex instruction set computing type of processor. So this is RISC type, that is reduced instruction set. So its feature is that very less number of instructions are there. So because very less number of instructions are there in such processors, so the advantage is that this particular processor can be highly pipelined. So you can design the architecture of such processor to be the highly pipelined. So we shall be discussing the shortly the architecture of this particular MIPS processor, which is highly pipeline architecture. So how pipeline is implemented in this processor, we are going to discuss. I hope you might have studied the internal architecture of some microprocessors like 8085 or 8086. So have you studied?
Yes, sir.
Okay, so uh, now you'll be studying here the architecture of this particular MIPS processor. Uh, so MIPS, it is a simplified version. It is a more realistic pipeline version, and it has got a simple instruction set, very less number of instruction. For example, for performing memory operation, only two instructions are there, like LW. LW stands for load word. SW stands for store words. There are arithmetic instructions: add, subtract, and, or, SLT. So these are the logical or the arithmetic instructions. Uh, and the control transfer instructions, they are BEQ and J. BEQ, that is branch if equal, and J is the jump instruction. So whatever program you need to write, so you need to make use of only these instructions, or these instructions are only available in the MIPS processor. So reduce instruction set computing. Uh, how is the execution of the instruction? So as you may be aware, in 8086 or 8085, uh, the program is stored in a memory called program memory, or it is stored in the memory, and there is some register called instruction pointer or program counter, which points to the instruction memory or program memory. and it fetches the instruction. The first step is to fetch the instruction. The next step is to read the operands. So your operands, they may be in the registers. Most of the time they are in the registers, so registers are to be read. Then depending on the instruction class, okay, which type of instruction it is, so it will perform the operation in the ALU, that is arithmetic operation. As far as this particular processor is concerned, uh, the memory address calculation, that is in the load and store instruction, the memory address calculation is done by ALU, whereas in 8086 or 8085, this particular operation, for performing this operation, separate bus interface unit is there. But ALU performs operations for almost all the instructions in case of MIPS processor. Then next step may be to access the data memory or to load or store the data. And the final step is to increment the program counter by 4, and it is stored back into the program counter so that the next instruction can be fetched. So this is one instruction cycle, and such instruction cycles, they are repeated so as to execute the program. So this is the simple architecture of the MIPS processor. You can see that there is a PC program counter, there is instruction memory. So input to the instruction memory is the address given by the program counter from where the instruction is to be fetched. So the instruction memory will send the instruction, uh, or it will the output of the instruction memory will be that particular instruction. The instruction will be decoded. So decoding unit, control unit, is it is not shown here in this particular diagram, so that the diagram can become simple. Based on the decoding, the appropriate registers are selected. Just a minute. So the uh, decoded instruction is available here, and the the appropriate, the contents of appropriate registers are read from the register file. So this you can call as a register bank or register file. I hope my mouse pointer is visible to you so that it will be easy for you to understand. I'm
Yes.
moving it. Oh, it is
Yes.
visible. Yeah.
Yes.
So the many registers are there in this particular register file. So contents of two register probably may be read, and they are available at the ALU, inputs of the ALU, and ALU will perform the actual operation. It may be arithmetic operation or it may be the logical operation, and the contents of that particular operation may be stored back into the register. Now depending on the instruction, always it may not be arithmetic or logical instruction, but if the instruction is related to the data memory, for example the store instruction or load instruction, so in that case ALU will be used to calculate the address of the data memory. So the one of the memory location will be selected, and data will be read from the memory. In the case if the data is read from the memory, then it will be read into some register of the MIPS processor. If the data is to be written into the data memory, then the data will be written from some register. You can see this particular line, from some register of MIPS processor, and that will go to the that will go as an input to the data memory, and it will be stored into the memory. So many memory locations are there, and one of the memory location is selected by this particular address, which is input to this particular data memory. Okay. So this is the simple architecture of the MIPS processor, consisting of the program counter, instruction memory, register file, arithmetic and logic unit, data memory, and of course two adders are there here. So the first adder is going to add just 4 to the contents of the current program counter, so that the address of the next instruction can be generated. But in case of the jump instruction or the branching instruction, the second adder comes into the picture, and that is going to calculate the address of the next instruction. So the next instruction will be leaving certain number of instruction, or the depending on the whether it is a forward jump or backward jump, it will appropriately add or subtract the number from uh, the intended address. Okay, so that will go to the program counter, and your program will make appropriate branch. So like this, the adders take part in the execution of the jump instruction. So this is the simple architecture. Of course, that particular architecture was very simplified, and you can expect that these particular lines, they are not just the lines like this. So here you can expect the multiplexers, okay, because output is coming from more than one source. Okay, so here the input to the PC it is coming either as the output of the first adder or output of the second adder. So you cannot simply combine it by joining the wires or buses like this. Okay, you need to have a multiplexer here. Here also, the contents into the register, it may come either from the ALU or it may come from the data memory. So whatever goes into the register, it may uh, go from either the output of the ALU or output of the data memory. Again, here input to this particular ALU, it may come from the instruction or it may come from the register. So like that, that is done in this particular diagram now. So you can see that here there are multiplexers wherever they are required. Okay. And of course, one more thing has been shown here, one more detail has been shown here, that there's a control unit. The purpose of the control unit is to generate the control signals. Okay, which are the control signals? For example, the register required a control signal, read write. The multiplexer need a control signal, whether to read from the register or to read from the instruction. Again, the ALU needs different control signal. Okay, just a minute, I'll be back within 1 minute. Okay, so uh, here this particular control unit is going to generate the control signals. So input to the control unit is the instruction. Okay, so depending on the instruction, whether it is arithmetic instruction or logical instruction, depending on what operation is to be performed, it may give appropriate signal to the ALU. You can see all the blue lines, they are coming out of the control unit. Okay, or it may be a store instruction or load instruction. If it is a store or load instruction appropriately for the data memory, it will generate the control signal, either memory write will be generated for storing data into the data memory, whereas memory read control signal will be generated when load instruction is executing and the data is to be loaded from the memory into the register. Okay, for writing the data into the register, this write register is uh, control signal is generated. Okay, and of course the other control signals, they are generated. So all control signals may not be shown here. It generates the control signal for all the multiplexers, uh, which indicates whether the contents of for example, this multiplexer based on this particular control signal will take the decision whether the output of ALU is to be forwarded to the register or output of the data memory is to be forwarded, like this. So getting this architecture of the MIPS processor, the different components which are present in this particular processor. Yes, I hope all the
Yes, sir.
students are actively listening. Hmm?
Yes, sir.
So once you are able to understand this particular architecture, then we shall be you will be able to understand the more complex architecture which is going to support the pipelining. Okay, so the main purpose of this particular chapter is to understand the pipelined architecture. Okay, so what is pipelining and how this particular architecture is converted to a pipeline architecture, that we shall study. But here, before that, you should understand the different blocks that are available here in the MIPS processor, and then we shall be able to study the pipeline architecture. Okay, so shall I move ahead, or you have any doubts in this particular architecture? I will be able to clear those doubt here itself. Yes, I hope you have understood this, and we shall go forward then. Yes.
Yes, sir.
Yes, sir.
Hmm. So I should get responses, otherwise I will feel that all of you have just opened it, hmm, started the meeting, and you are elsewhere. So I will skip some of the part here which is not immediately required. Okay, so let us directly go for the actual execution of the some of the instruction. Okay, so for that purpose, let me tell you, or let me show you one instruction which is of R type instruction. So uh, okay, so here on this particular slide, all the three types of instructions are there. So each instruction is of 32-bit. So first one is the R type instruction, that is register type instruction, and always it is arithmetic or logical instruction. Okay, the uh, bits 26 to 31 of that instruction, which is 32-bit instruction, they are always zero. Then bit number 21 to 25, they are used to specify RS register, that is source register. Okay, three registers are specified in the instruction. RS is the source register, RT is the target register, though RT is the name target register, but both RS and RT, those are the operands, which are the registers of which the contents are read. So the input operands are RS and RT. So the first register is specified using bits 21 to 25. So how many bits are there? 21 to 25. How many bits are these? Yes. How many bits are reserved for RS? How many bits are reserved for RT? And how many bits are hmm?
4 bits.
4 or 5?
5.
Count properly. So for each RS, RT, and RD, 5 bits are there. Okay, 21 to 25, including 21, you have to count. Okay, so 21 to 25 it is 5 bits. 16 to 20 it is again 5 bits, and 11 to 15 again it is 5 bits. So the register, every register is specified using 5 bits. So if registers have 5-bit address, then with 5 bits, uh, you can select one of the 32 registers. How many total registers are there with MIPS processor? There are 32 registers. So address of the first register is 00000. That is all 5 bits 0 is the address of the first register, and all 5 bits 1 is the address of the last register, that is 11111. Okay. So with the 5 bits, how many combinations of zeros and 1 you can make? How many combinations will be there of zeros and 1 with 5 bits? The combinations will be 2 to the power 5. Each bit can be either 0 or it can be 1. So 2 to the power 5, that is 32 combinations will be there. So one of the 32 registers will be selected by each of these registers. So 3 registers are mentioned here. So this RD register is for the destination. Okay. This SHAMT and function, it will indicate the appropriate function for the add instruction or subtract instruction or logical instruction. So depending on that, these will change. Whereas in the load or store instruction, you will have only 2 registers, RS and RT, and there will be a 16-bit address which is called the offset address. So that will be added to the base address. So RS register will indicate the base address, and to that base address of the memory, and to that address this particular offset address will be added. So a register is specified, the contents of registers are 32 bits. So 32-bit uh, address will, the base address will be added with this 16-bit offset, and the address of the data memory is calculated. So like that, the load or store instruction make use of the arithmetic and logic unit to calculate the address of the memory by adding the base address to the offset. Then RT register is used as the register, either the source register or destination register. In the load instruction, it is used as the destination register. The contents of memory will be loaded, will be read, and will be stored into the specified RT register. Or when in case of store instruction, the contents of RT register, it will be transferred to the memory, that is data memory, which is selected by the base address along with the offset. Okay, so this is like this. the load or store instruction will be there. The code for it is 35 or 42 hexadecimal. So that will be there. It will be there in this particular bits 26 to 31. Okay. Whereas 26 to 31 bit 4 indicates that it is a branch instruction, and that is branch if equal instruction. If the two instruction, these two register contents of these two registers, they are equal, then it will cause a branch. Otherwise, it will not cause a branch. And this particular address, 16-bit address, will indicate how many instructions are to be skipped, or how many instructions are to be skipped before or after the current instruction for branching it. Okay. So this is the this is how is the structure, you can say, of the MIPS instruction. So whenever instruction is fetched, you can see here this is for you can say R type of instruction. So the bit number 21 to 25 will be used to read the register 1. Bit number 16 to 20 will be used to read register 2 from this register bank. So the output of the read register process, so that will come at read as a read data 1 at this particular output, and the contents of the second register read will come out here as the read data 2. Okay. Then uh, the read data 1 is directly going to the ALU. Okay. Whereas this particular multiplexer will select read data 2. Okay. So appropriately, the control unit will generate the ALU source signal, so that the the second operand for the ALU will be coming from this only. Okay. That is register only. So ALU will perform the operation. It will get appropriate control signal. So ALU control will be there. So based on the ALU operation to be performed here, indicated with the blue line, it will be given the appropriate signal, and ALU will perform that particular operation. And the result of the operation, uh, it will be now, because the operation is the instruction is R type. So in the R type instruction, data memory is not required, because no loading of data or no storing of the data, so it is not required. So the contents, the output of the ALU, it will be given to this particular multiplexer, and this multiplexer will select the output of the ALU. Here you can see. Okay. So you can see here this uh, control unit is going to give the appropriate control signal to this particular multiplexer, and the multiplexer will select the output of the ALU, and it will be given, as you can see, this particular bus goes to the write data input of the register. So it goes here. So uh, data will be written into this particular register. To which particular register it will be written? So that is indicated by bit number 11 to 15. Bit number 11 to 15 will be selected here by this particular multiplexer, and that is the destination register. So destination register will be selected by this particular write data register inputs, and data will be written into it. Okay. So this is how is the execution of the R type of instruction. So you can see here the load instruction or other branch instructions. I will be back within 1 minute. Okay, so we shall you can go through this. So here data path for the jump instruction and other instructions, they are shown there. Okay. Now, let us come to the pipelining. Okay. Now, how this particular instructions will be executed in the pipeline mode, so that we are going to see. So before we actually go for execution of instruction in the pipeline mode, so let us first understand the analogy of a laundry. What happens in a particular laundry, how the clothes are washed, so that we shall see. So let us say there are a huge number of clothes in the laundry to be washed. So this particular huge number of clothes will be, because they cannot be washed at a time, so they will be divided into batches. So those particular batches are A, B, C, D batches. Okay. So the at 6 p.m. the first batch of clothes will be taken for washing. So let us say for each of the process, it may take half an hour. So the first phase is washing actually the clothes with the detergent. The second phase is the with the dryer. The third phase is to iron the press, to press those particular clothes. Okay, and the next uh, phase is to store or keep those particular uh, clothes at its proper place, or deliver it to the proper place. Okay, so so like this four phases are involved in that. So after the first batch of cloth is completed, then the second batch of cloth will be taken. Then again half an hour will be required for washing it, drying it, pressing it, and stacking it. Okay. So like that, the B batch of cloth will take another 2 hours for that particular purpose. So uh, 8 p.m. to 10 p.m. time will be required for this. Then C batch of cloth will be taken at 10 p.m. Another 2 hours will be required, so that will go up to 12 midnight. Then finally, D batch of cloth will be taken at 12 midnight, and by 2 a.m. they will be finished. Okay. So here each batch of cloth is taken independently. After one batch is finished, the second batch is taken. But if the laundry has got independent units, and if each unit is functioning independently, then how this can go? For example, the first batch of cloth will be taken and it will be given to the washing unit in the laundry. Okay. Then after the washing of the first batch of cloth is over, those clothes will be given for the drying unit. Now, when the drying unit is drying the cloth of batch A clothes, then the washing unit is free, and washing unit will take up the B batch of cloth. Okay, so between 6:30 p.m. to 7 p.m., drying of the first batch of cloth by the drying unit and washing unit will work on the B batch of cloth. Okay, so the processes, they are going simultaneously here for the different batch of clothes. Then at 7 p.m. what will happen? The clothes are A batch of clothes, they are dried, so they will be taken up for pressing. B batch of clothes are washed, they will be taken up for drying, and C batch clothes will be taken up for washing. Okay. Then what will happen at 7:30? At 7:30, A batch clothes which are pressed, they will be taken up for stacking. B batch clothes which are already dried, they will be taken up for pressing, and C batch clothes will be taken up for drying, which are already washed, and D batch clothes, they are taken up for washing. Okay, so this will happen between 7:30 to 8, and at 8 o'clock, uh, everything will be finished with batch A. So batch B clothes will be stacked, batch C clothes will be pressed, batch D clothes will be dried. Okay, so like this, the process will go on, and finally at 9:30, all clothes, all batch clothes, they are stacked. Okay, so you can see that how much time is reduced here. How much total time is required if this is done sequentially in the first case? Can you tell me how many total hours are required? 6 p.m. to 2 a.m. Each batch takes 2 hours, so four batches. So how many total hours?
8.
8 hours.
8 hours. So it takes 8 hours. Whereas it is done in pipelining, if it is done in pipelining parallelly, then how many hours are required? Then how many hours are required? 6 p.m. to 9:30 p.m.
3.5.
3.5 hours. Okay, only 3.5 hours are required. Okay, so almost uh, half of the time is required. Okay, so a lot of time is saved here when we use pipelining. Okay, so in the similar fashion, you can see that when the instructions are executed, so what happens normally is that if we don't use pipelining, then when the instruction is fetched, okay, so the operation with the instruction we can divide it into these five different steps. The first step is fetch the instruction, decode the instruction, or read the register and decode the instruction. Second step, execute the instruction, that is perform the operation in the ALU. Then access the memory, so perform some operation on the data memory, either read from the data memory or write into the data memory. And finally, write result back to the register, so write into the register. So this is the fifth operation. So any instruction may perform one or more of these particular operations. Okay, so in some of the instructions, some operation may not be present, for example writing into the register or reading or writing into the data memory, but almost first three are there in each and every instruction. So like this, any instruction we can say can be consisting of five different stages, and there are five different resources in the MIPS processor to perform these five different operations. But what happens is that after one instruction is completely executed, then only it goes for the next instruction. So it takes lot of time to execute that instruction. So you can see here that after one instruction is executed, which may take, let us say, 800 seconds. Okay, 800 picosecond. Pico means 10 to the power minus 12. So because the MIPS processor is very fast, so it executes the instructions in very less amount of time. Let us say 800 picosecond, one instruction is executed. So if we don't use pipelining, then after first instruction is executed, okay, instruction phase, decode instruction, then arithmetic read register, then perform operation in arithmetic and logic unit, then access the data memory, and then write into the register. So for this 800 picoseconds are required. If after we do fetch the instruction after the first instruction has been finished, then another 800 picosecond will be required for next instruction, and like this. Okay, but if we overlap this operation, that is after first instruction is fetched and read register for the first instruction is going on, we may fetch the next instruction. Okay, because instruction fetch unit is different than the register unit, arithmetic logic unit is different than this. Okay, so like this, if we overlap these particular operations by the different units, then it is possible that the instruction, the overall time that is required for execution of the instruction will be less. Okay, so we can speed up the execution of the program by using a pipelined architecture. Okay, so have you understood what is pipelining of the instruction? What is pipelining of the instruction? That is executing more than one instructions simultaneously. Got it?
Yes, sir.
Yes, sir.
Okay, so to do this, the architecture of the MIPS processor need to be modified. Okay, so how it need to be modified? Okay, of course there will be some problems because of this. There will be hazards. So we shall come to these hazards later on. Okay, or I leave it to you for study why these hazards occurs and how to overcome these hazards. Okay, uh, so here is how we do the pipelining. Okay, so first of all, what we do is that we divide the architecture of the MIPS into 5 different units. Okay, the first unit is instruction fetch unit. Okay, so you can see this particular dotted line. Whatever is to the left of the dotted line is the part of the instruction fetch unit. Then the second partition in this particular MIPS processor, it is instruction decode and register read register unit. Okay, so whatever comes in this part, it is ID, that is instruction decode and read register. Then whatever comes between the next two dotted lines is EX, that is execute unit. Okay, so it will perform either addition, subtraction in the ALU, or if it is load or store instruction, it will do the address calculation by adding the base address to the offset. Then the next unit is the memory access unit. So it will access the memory, data memory, either it will be read or it will be written. Okay. And finally, the write back to the register. Actually, for this particular unit, register is required, but actually register is required by this unit also. So what we assume is that the register is available here also, but actually register cannot be available in this unit and in this unit also. So we say that the register file or the register bank, it is shared by this write back to register unit and read register unit. Okay, so this particular register has to be shared by these two units. So how it will be shared? So it will be shared like for some time it will be used by for reading the register file will be used for reading the register for some time, and register file will be used for writing into it for some other time. Okay, because registers are very fast than the data memory or instruction memory, so the time required for instruction memory and time required for data memory access, it is more than the time required for accessing the register. So within the given time, some time will be given for the reading the register, and some time will be given for the writing back into the register. Okay, for example, for fetching the instruction, you need 200 picosecond. For executing the operation in the ALU, you need 200 picosecond. For accessing the data memory, you need 200 picosecond. But for actually writing back into the register or actually reading from the register, you don't need 200 picosecond. This operation can be done in 100 picosecond only. Okay, so like that it will be done. So this particular diagram shows that we have divided the architecture of the processor into 5 different sections. Okay, then at this particular junction of the the junction of the partition of this uh, MIPS processor, we need to introduce a register called pipeline register. Okay, so so as this particular architecture supports instruction pipelining, so between the instruction fetch and read register or instruction decode, a register will be placed. Okay, so what is the purpose of the register? It will temporarily store the bits. So IFID register, which is there at the partition between the instruction fetch unit and instruction decode unit. Then again, between instruction decode unit and execution unit, there is another pipeline register that is called IDEX. Okay, so this particular register will be used here. Then at the partition between execution unit and data memory unit, again one more pipeline register that is EX MEM, and between the write back and the memory unit, data memory unit, there is a partition, the pipeline register memory write back. Okay. What is the purpose of this pipeline register? The pipeline registers, they are going to isolate these particular units. Okay. And they store the state of the instruction. They store the state of the instruction. So how they store the state of the instruction? So that we shall see with the execution of one instruction. Okay. For example, uh, the let us say the execution of the LW instruction, that is load word instruction. So the contents of the instruction is actually there in the instruction memory. The address of the instruction is there in the program counter. So what will happen when the LW instruction comes for the execution? Then it will be fetched. So the instruction will be fetched. After the instruction is fetched, at the end of that particular cycle, the fetch instruction will be stored. It will be stored into this pipeline register. When it will be stored? It will be stored only after the instruction is fetched. That is, the cycle is completed. Okay, so you can see that after the instruction is fetched, now it is stored into this particular pipeline register. Okay, so the instruction memory need not keep need not keep outputting the instruction. Why? Because the instruction is already stored in the pipeline register. It is already stored in the pipeline register. So instruction unit is now free. The instruction unit is now free to fetch the next instruction. Getting this point? This is very important. The instruction unit is now free to fetch the next instruction. Okay, now what is happening with the LW instruction? The instruction is fetched and it is stored in this particular pipeline register, and it will be decoded. Now the registers will be read, and the decoded instruction and the registers read, it will be stored into this particular pipeline register at the end of this particular subcycle. Okay, so after that operation is done, instruction decode and read register. So it will be stored into this particular pipeline register. So it is stored in this pipeline register. So once it is stored, the contents of register read and decoded instruction, once it is stored in this, so this particular unit is now free. The instruction decode unit is now free, and it can work for some other instruction. By that time, this unit has fetched the instruction, so it will give that instruction here, and that instruction will be decoded. So this instruction decode unit will be able to decode that instruction. Okay, so these two units, they are free now. They can go for the other instructions, whereas uh, this execution unit will work for our original LW instruction. It will perform the operation on the in the ALU, and at the end of that particular subcycle, it will store the result into this particular pipeline register. So after it has been done, then the result will be given to the next unit. So the result of the this particular previous unit is stored here, and now this particular ALU unit, it may go for the other work, that is work of the other instruction. Okay, whereas the LW instruction work is now with the data memory. So appropriately it will load the data, and that particular address is already calculated by ALU. It appears here, it is stored in the pipeline register, and at the end of it, it will be it will be given to this particular it will be stored in this particular pipeline register, and in the last phase, this particular the contents of data memory read, it will be written into this particular register. Okay, of course, as I have already told you that this particular register file is shared by the write back unit as well as read register unit. Okay. So during the first cycle, it will be, or during the first 100 picosecond, the register file will be used by write back unit, and uh, in the second 100 pico second, it will be used by the read register unit. Okay, so like this, uh, the contents will be written into the register. Okay, so you can see here that when write back unit is writing here, so other units, they may be engaged with the execution of the other instruction. The instruction fetch may be you fetching some instruction, read register may be reading the contents of some other instruction, execution unit may be executing, performing operation in the ALU for some instruction, whereas the data memory unit will be loading or storing from the data memory for some other instruction. Okay, so like that, the execution of the instructions may go parallel like this. Okay, so with the help of this particular uh, with the help of this particular pipeline architecture. Okay, so that has been explained here. You can see the whole architecture is shown here, and this particular diagram, if you go through this diagram, then you will be able to see how the operations happen in parallel. Okay, so just to go through it, I will be back within 1 minute. So, any problem in this architecture, pipeline architecture? Have you understood this? You can see here that CC1, CC2, CC3, CC4, CC5, CC6. Okay, so this is one clock, and in one clock, uh, part of the operation of one instruction is being executed. So this is first instruction, second instruction, third instruction, fourth instruction, fifth instruction. So you can see at a particular time, uh, at this particular time, all units are being used. Okay, so if we go forward in this, then you will see that uh, all units are being used. Okay, particularly note this particular point, that during CC5 register register file is to be used by LW instruction also, and it is to be used by this another LW instruction also. Okay, so you can see the shading part here. You can see the shading part. So it is used uh, for this much time, that is half time, by LW instruction, and in the remaining half time, the register file will be used by this another LW instruction. Register file is being shared by two instruction. So got this?
Yes, sir.
So this particular unit, in this unit, this particular understanding the pipeline architecture is important. And the second part is the hazards. Okay, now when we go for the pipeline architecture, there will be hazard. That is, there will be problems. You cannot execute the program as it is, because there is a dependency of the instruction on one another. Because there is a dependency of the instruction, so before previous instruction is completely executed, you cannot go for the next instruction. And but here you are going for two three instructions simultaneously, up to four instructions simultaneously. So in that case, how to solve that particular problem? or what type of problem may occur. So that is the different hazard. So three types of hazards are there: the structural hazard, data hazard, and control hazard. So we shall have a short discussion on this tomorrow, probably at 10 a.m. tomorrow. We shall meet again for this discussion. Till then, you can go through the videos and PPTs and the uh, already I have shared with you the book for this. So the content of those books you can go through it. Okay. I shall enable all the tests. I think they are already enabled. If not, let me know. I will enable it so that you will be able to appear for all the tests of unit number 4, 5, and 6. I get the test they are enabled. Yes. So if you are not seen, just see it. If some test is not open, let me know. I will open it. So you have to appear for all the tests. So this Friday, Saturday, or you take a few more days because we need to compute your CIA. So before 10th, you appear for all the tests, or probably 9, 8, 9 by 8 or 9. You see that you have given all the test. After that, also, I will keep the test open. But your final marks are to be computed. So, any query in this now? Yes. Yes, was speaking. I did not get the query. Yes. Any doubt? Any query?
No, sir.
Hmm? Okay. So tomorrow again, if I do not have any other engagement, I will engage you at 10 in the morning. Okay. If I am not able to engage, I will put the message like that also. But by default, I think I do not have anything. So tomorrow by default, at least for 1 hour, I will engage. And after that also, uh, depending on how much time we get, I will conduct the required number of lectures. So for today, we shall stop now.